GPa pressures. You can see, so the A is for dry case, 50 water molecules, 150 water molecules. So you can see that the friction for quartz is much higher in the dry case, and then drops considerably low as more water molecules are added. So this is just showing that interfacial bonding between the tip and the substrate itself. Here in the dry case, you can see how the interfacial bonding increases with sliding time reaching steady state around 500 picoseconds. More interfacial bonds are formed, and the rate of formation increases as the load increases, which shows that it's a stress-assisted thermally activated process. Same again for the wet stuff. We can see that the bonding then increases as we add more water molecules. So for quartz, the bonding decreases as more water molecules are added, but for calcite, it actually increases. And we guess that's what causes the increased friction. So using these, so then we actually plotted the Arnhes equation that I showed you right at the start on that mechanical chemistry slide. We fitted these interfacial bond formations to that equation, and these black lines are basically showing the fit. So from these fittings, we can actually work out activation volumes for each system. So here on the top right, we can see it's the dry case, 50 water molecules, 150. And we can see that activation volume for quartz is much higher. So essentially what we plotted is the rate on a pressure scale, so rate against pressure, and then on a logarithmic scale of log rate or natural log of rate against pressure. We can see that quartz activation volume in the dry case is much higher. But again, as warm water molecules are added, the trend is reversed. Here on the left, we can see some of the interfacial bonds that we can see. So here is just the, so that's the diamond tip bonding with the oxygen molecule from the surface and the silicon. And here's a bunch of others. So this is carbon, hydrogen, oxygen, and then calcite. And yeah, just a bunch of others. I thought I'd show you, it looked cool. And this is basically how bonding controls the friction. So in the dry cases, you essentially saw that there was only one bond mainly forming, it's just diamond. So carbon here actually representing diamond in the tip, so surface, the tip surface basically. There was no bonding between carbon and silicon and carbon and calcium. So this is the main sort of trend we saw. And we can see that for quartz, there's a shed ton more diamond oxygen bonding, which is what we attribute a high friction to. So then we looked at the bonding in the wet cases and saw how water influences what we were seeing. And now we can see a bunch of different new bonds forming, like we saw earlier. So we have these little bridging bonds forming. So water actually facilitates these bridging bonds. So we can have carbon, hydrogen, oxygen, which then either bonds to silicon in the quartz case or calcium in the calcite case. And we also see carbon, oxygen, silicon. Oh, sorry, I already said that one. Carbon, hydrogen, oxygen, or carbon, oxygen, silicon. So basically, yeah, water bridges the two bonds together, and it creates it facilitates the bonding in calcite. There isn't much bridging bonds happening in quartz. The only thing that does happen in quartz is that the direct bonding between the tip and the substrate itself is reduced. So water acts like a barrier between between the tip and the substrate and prevents the direct bonding from happening, which then reduces the friction. Where the calcite case, there is still minimal direct bonding, but there's a lot more interfacial bonding or bridging bonds, which causes the increased friction. And same again with more water molecules, we saw that trend exaggerate. So again, quartz drops, calcite increases, and that's what causes the increased friction in the calcite case and reduced friction in the quartz case. Just to further emphasize that friction is governed by interfacial bonding, we can see here that the mean number of interfacial bonds was correlated with the mean friction force for the different systems and the conditions we studied. For the water present system, so this is A, 50 water molecules and B, 150 water molecules. We see that the mean friction force increases approximately linearly with the mean interfacial bonds for both diamond and calcite and diamond and quartz. We can see that the gradient is steeper for, oh, sorry, I said that wrong actually. So this A is actually diamond on calcite and B is diamond on quartz. My bad. So ignore what I just said for this slide. I'll start again. God. So diamond on calcite, we can see that the gradient is actually higher than it is for diamond on quartz, so that the interfacial bonds forming are at a faster rate, basically. So this is just further emphasizing our point, really, of what's going on. I think I've gone way over time. But just acknowledgements, just Daniel, Denny, thanks to James and Carlos. And again, thanks to Adri and his team at Penn State for the help with the Forster development, and my sponsors from Baker Hughes, Mark and John. Any questions, please feel free to ask or hit me up later on. I think I've gone over time, but sorry about that.
No, perfect. We're about 1 minute over, so we have time for one quick question while the next speaker is ready. So next speaker we've got is Dimitrios Mathas. Do you have a quick question?
What is it about the calcite, though, that makes it more reactive with water than the quartz?
That's a good question. We just saw that it was, so the water just basically facilitates or catalyzes these reactions. So essentially this bonding wouldn't have happened without the mechanical force applied. So mechanically, the tip slides over the surface when water is present, the tip breaks up the water molecules and creates these terminal bridging bonds. So we have I'm explaining with the hands, so we have a tip itself, an oxygen bridging bond, which is broken while the tip slides, which then can bond to the calcium. Because direct bonding between the tip and calcium itself doesn't happen in the dry case. Neither does direct bonding between the tip and silicon in the quartz system happen in the dry case. Only when water is present, these bonds can actually form because water is broken down as the tip slides over. So mechanical stress is applied and water is broken, and then we have these bridging bonds. And the bridging bonds that's more prevalent in calcium or in calcite than there are in quartz.
Well,
that makes sense?
Thank you, speaker. Thank you. Okay, so if we go on to Dimitrios Mathas.
All right, I need, okay, now I can share my screen.
Thank you.
Screen. So, can you see my screen?
Yes.
Right, let's switch full mode. And screen pointer. Laser. Can you see the laser pointer?
We can, yeah.
All right. So, hello everyone, my name is Dimitrios Mathas, and today I will talk about my research where we evaluate methods for calculating viscosity for lubricants at different operational conditions. I would like to thank the organizers of this very interesting named SIG meeting. So this is the outline of the presentation with the motivation of our work, and then the theory of equilibrium and non-equilibrium MD for calculating viscosity. This will be followed by some of our results and its conclusions and our current work. So why are we doing this kind of research? Well, there is clear industrial interest in calculating the rheological properties of lubricants at operational conditions and by varying temperature, pressure, and shear rate. And the main applications for this is the automotive industry and others, such as aerospace. At times, it can be challenging and expensive to calculate those properties, and this is where computer simulations can offer a helping hand. And also, this kind of research falls into the category of digitalization, which is quite a modern topic. So the first method for calculating viscosity is the equilibrium Green-Kubo method, which calculates viscosity as by using the integral of the autocorrelation function in 3 dimensions. Alpha, beta are the Cartesian coordinates. P is the pressure tensor. And we use the autocorrelation function of the pressure tensor, which is obtained by the ergodic hypothesis as the time average, which is also then discretized by it's equal to the ensemble average. And Tmax is the total simulation time. So for EMD, there are 2 layers of convergence. The one is the convergence of the autocorrelation function, which is discretized and can be noted by the C value and is calculated by the ensemble average. And S is the interval of the pressure tensor, how often we use the values. And P is the total number of correlations we have. D is a fraction of simulation where we perform the correlation. And N is the index of the C values. As we can see in this example here for benzene, we have a correlation function which decays to 0. And what we want is to calculate and integrate the long tail, which in some cases it's not easy to converge, or it doesn't converge at all, especially at high pressures. And this is what I'll show you later for this method. Now, the second method for calculating viscosity is called non-equilibrium MD, and the idea is that we use perturbed equations of motion by imposing an external shear field. And one algorithm, this load algorithm that we've used, is an efficient algorithm for setting up wet flow in order to calculate viscosity. Now, in order to calculate the viscosity, we perform simulations at different shear rates, and viscosity is obtained by its definition by dividing the pressure tensor over the applied shear rate, and the shear rate is calculated by dividing the velocity applied at the top edge of the simulation box and the y dimension of the box. And what we want to obtain is a graph similar like this, where there are two distinctive regions: the Newtonian region, where viscosity does not depend on the applied shear rate, and the shear thinning region, where there is a linear behavior, the linear behavior relationship between the viscosity and shear rate. And then we apply zero shear rate extrapolation to obtain the Newtonian viscosity, as was also mentioned in previous talks. Now, this is an example for an NEMD wet flow using lamps, and this is an example from our simulation where we used 179.10 dimethyl molecules. And this is taken from our recent paper, which was accepted in tribology transactions recently. So periodic boundary conditions are enforced in all dimensions, and after applying the slot algorithm, we have a linear velocity profile as we deform the simulation box. And this is a bulk NEMD simulation. Now, the software that we use for our simulation consists of processing and simulation software. So for processing, we use those open source programs, PacMol and MolTemplate, to scale the single molecule, the number of molecules we wanted, and MolTemplate converts the output of the previous program to a LAMPS readable format, whilst allowing us to select the force field parameters. And we use LAMPS with the classical molecular dynamics simulation, with the classical molecular dynamics code, and can be used for many calculations. And our example is viscosity. Now, the overview is that for our simulation is that we use the 9.10 dimethyl molecule, which is a component of the PO2 base oil dimer, and we calculate zero shear and shear viscosity for a range of pressure up to 1 gigapascal and temperature in the range of 40 to 150 Celsius. And we applied shear rates of the order of 10 to power 6.5 to 8.5 inches seconds. And we calculated the viscosity with EMD and NEMD. We compared the two methods with experimental data, and also we examined the force field we used. We used the LOPLS, which is a long optimized potential for liquid simulation and all atom force field, and the general Amber force field, which is a more general force field. And the number of atoms is around 10,000, and the starting simulation box had the size, it was a cube with a dimension of 65 angstrom. And the production run for viscosity for each method was 40 nanoseconds. Now, this graph here shows the viscosity at 40 Celsius for the pressure range. On the x-axis, we have the logarithm of the applied shear rate, and the y-axis we have viscosity. Squares are experimental value for PO2 lubricant, and circles are the simulation results with LOPLS, and triangles are the GAF results. And overall, there is a good agreement with the experiment, and the average lines are in a Newtonian regime, and viscosity was calculated by the average, while at the higher pressures we have a shear thinning region, and we extrapolated to zero shear rate by using a Paul-Haring model. to acquire the zero shear viscosity. Then in this plot we also saw the pressure viscosity behavior for the two methods, and on the x-axis we have the pressure and the y-axis logarithm scale of viscosity. Now the orange circles are the EMD green cubo method, while green is the NEMD with LOPLS, and yellow are results with GAF. And what we see is that after the point of around 0.4 gigapascal, EMD fails to calculate, to obtain a value of the experimental value of viscosity, and this is because of the autocorrelation function not decaying as the relaxation of the molecule relaxation time increases dramatically, and the ACF does not converge, while the NMD method performs much better, while the general ambient force field performs not as good as the NMD method. So we conclude that NMD can capture high pressure viscosity, while EMD are not very accurate at high pressures and viscosities, and this is also taken by literature, statement, and literature. So to conclude, EMD is not ideal for very viscous molecules at high pressures, and this is because the high relaxation time hinders the decay of the ACF. Calculating viscosity is not a straightforward process, and it's demanding. NEMD simulations allow us to calculate viscosity at high pressures, and we believe it's a reliable approach for computing it. And also the use of force fields is very important to choose an accurate force field. Currently, we are performing confined NEMD simulation by examining again LOPLS force field and the REACT-FF force field, which was mentioned previously. And we use we have a surface of iron oxide, and we include the same lubricant, and this is taken by UN's open source program, LAMPS Builder, which is available here, and it's open. We modified the code to include our lubricant, and this code can be modified to include any lubricant. And we examine the different applied pressures at the top, and we shear, and we will calculate viscosity with those force fields. At this moment, I would like to acknowledge my supervisors from Southampton University, Professor Chris Galaris, Professor Ling Wang, and Professor Walter Holviger for useful discussions. I would like to acknowledge the use of IRIS-5 supercomputer and Yang from the MMM Hub. I would like to thank our colleagues from Cepheler. I would like to thank Dr. Scott Bayer from Georgia Institute of Technology for experimental data, and also from Imperial College London, Dr. James Ewan for useful discussions we had. I'd also like to thank all of you for your attention, and any questions, please let me know. Thank you very much.
We have a round of applause for them. So, yeah, thank you very much, and thank you for sticking to time. So, who would like to ask the first question? So, I mean, I guess I'll ask a question. I mean, I guess you've talked to James about ways to get viscosity. Did you try any of the other kind of techniques to improve the viscosity calculation from the kind of equilibrium methods? So there's various techniques that try to kind of fit a form. You found that they were not as effective as the NEMD ones?
I believe you refer to the time decomposition method for EMD, for example.
Yeah, there's various flavors of different techniques, but you found that nothing was as good as the NEMD.
Yes, we firstly started with EMD, and then we switched to NEMD, and we didn't try the time decomposition method, but we think they wouldn't improve the results so much. And in our paper, we have some details on how we obtain the autocorrelation parameters for EMD, and yeah, it does not converge at higher pressures. Even if we fit a function and to the data, it won't improve that much.
Okay, so it's not better than that. Okay, brilliant. Any other questions before we move on? Yes, please, Carl.
Hi, thank you for that talk, Dimitrios. Really enjoyable. Couple of little questions. Have you tried constant stress NEMD, which might be more appropriate for these high viscosity sluggish fluids or glassy type materials?
So constant stress. I'm not aware of this method. I know there's NEMD, there's RNEMD, like reverse. Would you elaborate? What do you mean by constant stress? You mean the? Do you mean the ensemble or? No?
Yeah, well, in normal Couette flow, for example, you apply a strain rate and measure the stress. So you do the reverse here. You apply the stress and measure the strain rate.
Yeah. So I think you refer to the. This is called, I think, reverse non-equilibrium MD.
Yeah, but I'm not referring to the Muller-Plath method. This is just straightforward application of Doll's tensor again. If you look in Evans and Morris, chapter 6, it describes the constant stress algorithm that you could try.
We use the slot algorithm, which is implemented in LAMPS. We haven't. I'm not sure if this is implemented in LAMPS, and this is why we're using the main program we're using is LAMPS. So
right. The other question was, when you're calculating your green Kubo integrals of the stress autocorrelation function, can you show me that equation again?
Yes, the equation is here.
Yeah, so you are using all 9 elements of the stress tensor in that correlation, are you?
So we're using the non-diagonal elements. So there are 3. This is in the, we use the XZ, XY, and ZY. So we don't use all the 9. We use the 3 of them.
Yeah.
In theory, there are 6, but there are 2 of them. They are the same. So XZ is equal to ZX. So it's 3.
Yeah, because there was a paper by Peter Davis and Billy Todd, and I suspect they've gone offline now. If they're in the audience, they might chip in and add something. But they produced a paper where they showed that you get a better viscosity if you use all 9 elements. Now, you're right, they're not all independent, and you can account for that in the weighting factor, but you will improve the signal to noise quite a lot if you use all 9 elements of the viscous stress tensor.
Yes, I've read about this. I've read some papers where they used all of the 9, and we use the LAMPS implementation, which uses 3 of them.
Right. Seems you're hog-tied by using LAMPS because you're having to use whatever features it has available. But if you don't mind a bit of programming and getting your hands dirty, you should try writing your own code to try these ideas out, and then
so basically
use that to put pressure on the LAMPS writers to include those features.
After a point we developed our own Green Kubo our code. So we started from their code, their implementation, and I wrote the autocorrelation. We wrote an in-house code, and for sure we could extend this and try to use all of the elements.
Yeah, I must admit, I'm not a big fan of LAMPS or any of these packages, because I once tried it for Couette flow of a WCA fluid and got different results to what is in Dennis Evans's book, and different results, and results of which I agreed with an independent calculation. So there's something funny about LAMPS and how it deals with Couette flow, and I think it's due to the thermostat, but no one's really got to the bottom of that. So I personally, I don't trust LAMPS for anything NEMD.
I think that's definitely a good topic for discussion within the session. And on that note, we're about 5 past, so I'm very aware of time. So if we could thank the speaker again, I know there's a couple more questions, but if I could ask them to wait for the discussion, and then we can have about 20 minutes of questions then. So our next speaker is James Sprittles.
Hey.
We're talking about noisy interfacial nanoflows.
So hopefully that's shared, Edward.
Just still dark screen, but I think we'll.
Can you see that?
It might be loading. I think we've got a blank screen at the moment. Yes, perfect. There we go.
Okay, good. So thank you for the invitation for this nice day. I've really enjoyed a lot of the talks I've been to today. I'm going to be talking slightly differently, more about more from a fluid dynamical kind of continuum perspective, trying to interpret some of the things which we see in MD with macroscopic equations. So just to give you some motivation for looking at interfacial nanoflows, some of the applications I've been involved with, for example, looking at how coalescing microdrops can extract heat from surfaces. And Sri Hari in Edinburgh with Matthew did some work on the nanoscale equivalent there. There is increasing possibility to nano manufacture, so to create topologies on the nanoscale using de-wetting of films, and the possibility to use classical instabilities, which I'll talk about later, to create things like nanoparticles. So the underlying flows in these and many other processes are things like coalescence, so that's the joining of liquid volumes, the breakup of thin films and subsequent pattern formation, and the breakup of liquid volumes. So from my own kind of applied maths background, much of the interest in these has been in finite time singularities. But I guess from a more practical perspective, people are interested in understanding how these processes work. And an obvious thing to say is, well, why don't we just do experiments? So the point here is that these are on millimeter scales. And if we're interested in nanoflows and nano drop dynamics, for example, we can't see them. So to be a little bit more careful, we can often see spatially using AFM or SEM or these kinds of techniques, but we can't simultaneously resolve the temporal and spatial scales. So our approach is that we're going to use molecular dynamics as a virtual experiment. It's not my area of expertise, but I work with people who do use it. And in some sense, molecular dynamics gives you absolutely everything you need. Everything is built in there. You have viscosity, you have surface tension, you have thermal fluctuations and all these things. But as we're all aware, these are incredibly computationally intensive. So, for example, if we look at the kind of simulations that Matthew's group were performing in Edinburgh, to coalesce 220 nanometer water drops is right at the kind of edge of our capabilities. So the hope is we use MD as an experiment, but we can develop new models of classical fluid dynamics. And crudely, we can think of Navier-Stokes plus some nano stuff. And the nano stuff I'm going to be talking about today is how to incorporate thermal fluctuations into this classical framework. Okay, so all of this started with two PhD projects, I guess around 5 years ago now. There was Sri Hari in Edinburgh, who's working with Matthew and Jason at the time, and then Chengxi in Warwick. So the idea was that they would look at these two canonical problems of drops coalescing and jets breaking up. And my hope was that actually they would find something interesting about the singularities which occur in the classical equations. But as you'll see, we ended up doing something completely different. So the first thing which Sri Hari noticed was that nanodrops don't always coalesce where you'd expect them to, or where I would expect them to. So on the macro scale, you have typically drops of spheres, you press them together, and they join along their lines of center. But here we see very clearly that drops can coalesce off center. And in fact, there can be multiple initial contacts. And the reason is that nanodrops aren't spheres. So if we sit and we just watch one of these nanodrops or a quasi 2D drop, we see waves traveling around the interface driven by the thermal fluctuations within the bulk. So these are nanowaves on a drop. And so if we take some instantaneous snapshot, clearly we don't have a circle or a sphere. We have some other shape. And if we push these shapes together, there's no reason why they should join along their lines of center. If we average in time, then we get back to this classical picture of spheres or circles. Ed, can you see my cursor, by the way? I don't know. Okay, so I'm waving it around. I'm waving it around like everyone can, but I might be just waving it to myself. Now I know. Thanks.
Okay.
You're also massive, by the way, Ed. So don't pull any funny faces. All I can see is your huge face in front of me, and the PowerPoint slide. Oh, you've gone now. Okay. So, so that was nanodrops and coalescence. What about nanojets? Well, things were well known there already. On the macro scale, you see this classical picture of jets breaking into drops and satellites in between. So kind of drops and threads. And on the nanoscale, you see something completely different, where you just get this kind of double cone type breakup. And this was understood by Mosler and Landman in 2000, and they attributed and showed why this can be attributed to thermal fluctuations. So this might be well known to some of you, but I think it's quite nice to develop things first in thermal equilibrium to kind of get some understanding of what we're looking at. So a kind of bit of background, it was the early 20th century that many famous physicists and mathematicians looked at Brownian motion. And it seems to be Smoluchowski who first realized that if we have bulk random motion, then we should be creating waves at interfaces. And then Mandelstam in 1913 derives their properties in this paper. And essentially what I'm going to do is reproduce the arguments from here. So a lot of what I'm going to be talking about today is concerned with thin liquid films on solids. And the MD we do in this case is essentially quasi 2D. So we have a very thin length into the page and not much varies in that direction. So I can think of this interface being parameterized by some height, which is a function of x and time. And the obvious thing to do is to take some average height and perturb it with something small. And given that in MD we have periodic domains with some length Lx, we can write this as a Fourier series. And what we're really interested in is what these coefficients are. Now, this is something that's fluctuating, and so we only really expect to be able to derive the statistical properties of these things. Okay, so the argument we make is an energy one. We say, what is the extra energy associated with these waves appearing? And the energy is going to be proportional to the surface tension times the area. And the area is just going to be the length into the page times the arc length of this interface, okay, which has this formula. And then we take off the flat case, if you like, to create the extra energy. So we can Taylor expand this for small dH dx. We get this expression here, substitute this into here, and we find the energy associated with each mode. Okay. And now we can use a bit of physics. We can say, well, we know that the average energy, ensemble average energy associated with each of these modes is kT over 2. And that gives us, therefore, the average, ensemble average of these coefficients. So essentially the variance of these coefficients, which tells us roughly how much this interface is fluctuating. Okay, so we have this expression here. And out pops this length scale, which is kT, which you can imagine is trying to kind of push this interface away from equilibrium, divided by the surface tension, which is constantly trying to get it back to flat. And for something like water, that's less than a nanometer, and that's why we have nanowaves on these scales. Okay, so what I'm going to be coming back to time and time through the talk is the spectrum. So that's the spectrum of the waves on the interfaces. Mathematically, it has this expression. So it's the Fourier transform of the perturbation squared, average, square rooted. Crudely, we can think of it as telling us for a given wave number at a given time, how big is that, the wave associated with that wave number and how will it develop in time. And what we've just done essentially is derive that expression for the equilibrium case, for thermal equilibrium. So we found this expression on the previous page. And so we know that the equilibrium spectrum looks like this. You see there's no time dependence. It goes like 1 over k, and it's proportional to the length. And that's basically because the longer this domain is, the more waves we can fit in, so the larger the amplitudes. Okay, so what we do is we start the MD with a flat interface, and then we watch the development of these waves. So just to mention, this is capillary wave theory. This is a very well established topic. So we watch the development of the waves in the MD, we extract the surface, we calculate this quantity, and here you see an ensemble average of this developing in time. And you can see it's tending towards this equilibrium expression, which is this dashed line. But what we're really interested in, which I'll talk about later, is how to capture the development of these waves, so the dynamics of the interface. So from this, we can calculate various properties. We can look at, for example, the variance of the interface, the kind of roughness of the interface, if you like, has this expression. We can expand. We know what these coefficients are. And so we come out with a nice compact expression, which looks like this. And then in 3D, we have something similar, except for now, due to the appearance of a logarithm, we need cutoffs both at the small scale, which you could think of as the size of the molecules or some correlation, and at the upper scale, which could be the length of the domain, or it could be boundaries or capillary length or various things. Okay, so the nice thing is that actually the things which we saw in drop coalescence, we can describe relatively easily with thermal equilibrium. So what Srihari had noticed was this off-center coalescence, and what we'd like to understand is over what kind of length scale can this coalescence occur. And the person who really developed the theory for that was Makita in Warwick, and he basically took a cylindrical and spherical alternatives to the geometry I've just shown you. So you take a sphere of radius r and perturb it, and then you can find out the variance associated with this perturbation. And these are those expressions. So Srihari validated these against his MD, which was nice. And then the argument we made was actually a rather simple one. We simply said that if we focus in on here, we have some fluctuations and we have a rough estimate for their size, which comes from the variance. And we know the typical height of the interface because locally it's on average parabolic in here. And so if we equate these two expressions, we should find over what distance coalescence could possibly occur. And if we do that, we find this nice expression here. And so actually out pops the thermal length scale and the radius of the drop. And what's interesting is if we took a macroscopic drop, so say a millimeter, this would give us around a micron. So this nanoscale effect can have a rather larger influence on drop dynamics. Okay, so on to dynamics. Obviously, to consider dynamics, we need equations of motion. And those have been written down a long time ago by Landau and Lifshitz. And their idea was, well, let's just take the Navier-Stokes equations, incompressible, isothermal in this case, as we're used to, and let's just add a fluctuating stress onto the end. Okay, so this fluctuating term must have average 0, and correlation takes the following form. So let me just explain this form. Essentially, the Kronecker deltas here give the form of the tensor we require. The Dirac deltas just simply say that these fluctuations are uncorrelated in time and space, and this prefactor is just required to satisfy fluctuation dissipation. And when we take this in 2D, essentially we average into the page and the Dirac delta becomes a 1 over length. Okay, so fluctuating hydrodynamics is increasingly popular. People are using it as a kind of mesoscopic approach to capture fluctuations in a computationally tractable way in things like chemical reactions, mixing, various biological processes, and interfacial flows. So we're going to do something even simpler and actually start by looking at lubrication equations in 2D. So this is the classical setup for lubrication type flows. So we have incompressibility, we have X momentum, and we have Z momentum. And here we've exploited the fact that this is a long, thin geometry to reduce, to take the leading terms, essentially. So for a start, we're going to apply no slip. We have kinematic equation and the balance of pressure with surface tension at the interface. And the new terms which transform this from a PDE to a stochastic PDE are these terms appearing here. So I'm not going to go through the derivation today. It was first derived, the stochastic PDE associated with this formulation was first derived by Grun in 2006. These first two terms are just the classical lubrication theory, which says that the squeezing motion due to the height is balanced by these the flux, which comes from pressure gradients, with a mobility from no slip. And this extra term here is due to the noise, if you like, the thermal fluctuations. And all I've done is take all the nasty terms out and put them in the prefactor so that noise has variance 1. Okay, so this equation has been considered in a number of different contexts of increasing popularity. And what we really wanted to look at was how this affects the stability of thin liquid films, because in a sense, the case of most practical interest is when you put a thin film down on the solid, is it going to stay there or is it going to break up into drops? And that's what we were looking at. So what does the noise change? So this was our stochastic lubrication equation. We can simply apply a linear stability theory. So we just take some average height and perturb it, linearize the equation, transform into Fourier space, and that gives us a much simpler looking equation to solve. And from that, we can show that there is a deterministic and a fluctuating part to the development of waves. The deterministic part just has this usual A to the omega t type expression. The fluctuating part looks a bit nastier, but we can derive from that the spectrum. And this was first done by Mecker and Rauscher in 2005. So the spectrum, the development of these waves looks like as follows. And you can see it's a function of wave number or wavelength, if you like, and time. Okay, and it's analytic. So this was the development of the spectrum I showed you from MD earlier on. And that is now our new theory, or the theory, showing how the stochastic lubrication equation predicts this development. So it's kind of okay-ish. It predicts some of the key features. So for example, you see the fastest growing modes change in time, which is a non-classical feature due to the fluctuations. But clearly the agreement isn't great, particularly at these later times. And that's no real surprise because we use no slip, and we know from both our MD and from a huge amount of literature that we usually have slip, and that Navier slip can describe it relatively well. So what Yixin did was extend our model to account for slip. And if we do that, we can see much, much nicer agreement. Okay. If you look very carefully, you can still see in here that there is not so great agreement, and that's because the wave numbers or wavelengths are around 1 here, and that doesn't satisfy the thin film assumption, the lubrication framework. So we've done further work where we use a Stokes analysis, and we can actually capture this behavior as well, but I don't have time to talk about that today. Okay, so what we were really interested in was when these films break up, and the classical way to induce rupture is to add disjoining pressure to the formulation. So that is essentially gives you an additional term which looks like 1 over the height cubed with the Hammaker constant on the top. And what that means is that the growth rate can be both positive and negative. And clearly the crossover between the two is when we see instability. So if we calculate when omega is 0, that happens for small wave numbers or large wavelengths, which need to be larger than this quantity. And then from our MD perspective, what that means is, well, if we want to fit one of these waves in, we better have a domain that's long enough. So the simple experiment which we thought we'd do is let's take an MD domain that is shorter than the critical wavelength and check that we have stability. And we don't. Okay, so this is actually not that surprising because the arguments I've just given you have nothing to do with fluctuations at all. And fluctuations are really, really important at these scales. So a different way of looking at this is to look at the spectrum and say, well, my critical wave number is where the spectrum is growing. So that can be defined by the time derivative of the spectrum being 0. And if we do that, then we find a new expression, which is both the classical part plus a new part, which depends on the noise, essentially. And then we get a completely different expression for the critical wave number. And you can see why a film of this length will rupture. Okay, so kind of going back now in time, but going forward in complexity in some sense. Another interesting thing is to look at the breakup of liquid cylinders or jets, and that's essentially the Rayleigh plateau instability. So this was Cheng Shi's PhD project. And the formulation is very similar to before, except for now we're not in a planar geometry anymore, we're in a cylindrical one. So we have radius, which we have to worry about rather than just height. And the equivalent equations were derived by Mosler and Landman back in 2000. They took the usual form of the deterministic equations and added noise in the correct way. And what they showed in that paper was kind of remarkable. They showed that MD shows jet profiles that look like this, with this very kind of iconic cone-like, double cone-like profile. Lubrication equations with no thermal fluctuations show something completely different with long threads appearing. And yet this stochastic model they derived captures this cone-like behavior very nicely. What was interesting, though, is they hadn't actually looked at the stability of this problem. They only looked at the final stages of breakup. So what we thought we'd do is just look at the instability problem, which is well known as the Rayleigh plateau instability. That, just to recap, plateau essentially showed that it is long wavelengths and short wave numbers which are unstable. And then Rayleigh calculated the fastest growing mode. Now, to adapt this for the nanoscale and to capture thermal fluctuations, we took the stochastic lubrication equation, and Duncan derived the spectrum in a very similar way to we did for thin films. And again, you have an analytic expression for it, which allows us to compare to MD. So the MD that Cheng Shi did was very simple. Take long cylinders of liquid, watch the waves develop, and measure their properties and compare to the theory. So this is the MD after averaging. And this is the deterministic model. So you can see the deterministic model, the instability growth is far, far too slow. And yet when we add thermal fluctuations, the agreement is remarkably good. So this was published a couple of years ago now, and Cheng Shi did some nice artwork, which was featured on the front cover of JFM. So very similar to what we saw for planar films, what thermal fluctuations brings is the appearance of short wavelengths which can dominate. And so the idea here was, can we rupture this plateau instability criteria and actually rupture fat threads, if you like? So we took threads which were shorter than the plateau criteria for stability. And indeed, in MD, you see that they can break up. And then the question is, well, the fatter they are, the longer it takes for thermal fluctuations to be able to break them up. There is some waiting time associated with this, which we have from MD. How can we describe this analytically? And that's what we're working on at the moment. So the final part is to say, well, everything I've actually done so far with the fluctuating hydrodynamics is analytic, and that's a lot easier than numerics in some sense, because there we have to worry about how to represent the noise. So our recent work is to try to access the nonlinearities in breakup and compute the stochastic lubrication equation. So the crudest thing one can do is simply say, well, let's make the noise just some random numbers on a grid with normal distribution and the appropriate scaling. And remarkably, this actually captures the linear stages perfectly well. But what we saw when we go to non-linear stages is that this scheme basically gets destroyed and we have no notion of convergence whatsoever. And for anyone who works with stochastic PDEs, this is no surprise at all. So what we introduced is correlations within the model. So we, in the first instance, we just simply introduced the correlation length and timescale and interpolated between them. But more recently and more properly, we project onto an appropriate basis. So if we do that, then we can actually, we have some notion of convergence in space and time, which makes me very happy. So these show the breakup profiles converging as we refine the grid. We can agree nicely with molecular dynamics, as you see from these profiles. And now the really nice thing is we can compute and compare, for example, deterministic rupture to stochastic rupture for the same parameters. And what you'll see here is that the stochastic case has these nanowaves on and breaks up in this double cone quite quickly. And the deterministic case takes much longer and has this thin thread in between. So this is just a qualitative comparison. It's not for the same parameters in this experiment, but qualitatively we see the right things. So the hope is that we can take these fluctuating hydrodynamics models and use them in cases which are inaccessible to an MD. So we can take them from the millimeter scale down to microns and nanometers, and they're much faster than the equivalent MD. So I think that's all I have to say. I should acknowledge the various people involved in this work and the various funders, and I'd be happy to take any questions.
Oh, thank you very much, James. So just to know, you're not going to be around for the discussion session. So
I'm afraid not. People can obviously email me, though, if they want to easily enough. I'll be happy.
Fantastic. But yeah, we should have questions now. So please ask. Who'd like to go first? Mike. Oh, yeah. Okay. Jasper, please.
Yeah. So thank you, James, for a really interesting talk. Fluctuating hydrodynamics is always really, it's a really nice theory, I think. So you do assume instantaneous incompressibility, I guess, in what you're doing. So and I know, you know, these capillary waves are often modeled in this way, but intuitively, I would imagine that on these fair scales and small scales, that compressibility effects or density variations or fluctuations can also induce some sort of instability on the surface. But I don't know if you have any knowledge about anyone looking in this direction. I mean, it does give another degree of freedom, and then you all of a sudden maybe can fit the data a little bit better. I don't know, but it's. I was just curious.
Sure. I mean, looking at the estimates we've done and from the kind of good agreement we get for the cases we've looked at, I don't think compressibility is important. The place I've seen it occurring where it does seem to be important, and probably other people here will be able to comment better than I do, is on things like nucleation and phase change and things like that. So I've seen some nice works on vapor bubble creation and such things where density fluctuations are really key to the whole thing, the whole fluctuating hydrodynamics framework. But for these cases, I think if you do either the kind of continuum estimates from your PDEs or you just measure the things from the MD, I don't think compressibility is so important.
Yeah. Cheers.
Thanks.
Carl, is that an old hand or do you have a question? I think you're muted still.
That's an old hand.
Old hand. Okay, brilliant. Anyone else? Questions? I mean, I had a quick one on your fitting to the H surface. Well, your definition of the surface you did in terms of kind of sine and cosines. And then you moved on to the spherical case. Was that using spherical harmonics or some other basis set when you did it?
Yeah, absolutely. Yeah. Yeah, of course. Yeah. I mean, all of the kind of bases are just the same as you would have for a classical oscillating drop. So you know what they are for cylindrical, you know what they are for spherical. They're obviously the harmonics that you require.
Did you then fit that to the molecular system? It's just because, I mean, obviously for the flat interface, that's reasonably straightforward, but I think it's quite difficult to work with spherical harmonics in a molecular environment. Or, as in, did you manage to actually?
So the fitting was all for the quasi 2D drops, so they would have been averaged into the page. I'm sure Sri Hari was here earlier. I don't know if he's still here to comment on if he knows precisely how it was done, but I don't remember exactly how he did the fits, which isn't very helpful, Ed, I'm afraid.
No, it's fine. I mean, I imagine it's just details, but then from that you then get this kind of relative magnitude of the two scales. I mean, is that using kind of asymptotics to get that, or?
Or do you mean in? Go on.
So you had the logarithm of L over some smaller length scale, essentially, from that process.
Yeah.
And so I missed the step where you got that. Was that basically from?
So that was for the cylindrical case. If let me just check which one you're talking about. So here we are. So which case is it you're interested in?
Yeah, I mean, to be honest, any of these ones where you get that kind of form.
So the spherical one's really boring in some sense. It's the same as the planar 3D case, except for your cutoff is no longer the length of the film. It's 2 pi r roughly, crudely. So it's the perimeter, because this thing is, you can think of it as like a planar film that's periodic in some case, and the period is obviously going to be 2 pi r.
Okay.
The cylindrical case took a lot more work, because there you have r, which is the radius, and L, which is the length of the cylinder. But the reason we needed to do that is we wanted to verify, because quasi 2D drops are much computationally less painful than doing the full spheres. We needed the expression into the page as well as around, if you like. So that was the real work which Makita had to do in deriving that. And there you have waves into the page and around this circle, if you like.
Okay, interesting.
I don't know, Edward, if that, I'm Srihari. Sorry, I was away from my laptop when James called my name. I don't know if that answered your question.
Yeah. I mean, it's just interesting.
Well, part of the question, Srihari, is how you actually took the interfaces. So to calculate this dr squared in the bottom right hand corner.
Yeah.
How did you measure the interface?
So I'd measured the location of the spatial coordinate where the density fell to half of the vapor and liquid density. So I did average into the page. But for taking that average, I took a slice, which is like half a nanometer thickness. So it was not complete. So the thickness of the cylinder that we used was like 4 nanometer, but we didn't do a complete average along the axis, but only to like 0.5 nanometer thickness.
Okay, brilliant. Thank you. I'm very aware of time now. So do we have any other questions? Just quickly, or if not, we'll thank James again and move on to our next speaker. Thank you. So that's Lorenzo Botto, talking about graphene, nanohydrodynamics, non-equilibrium MD, simulation of graphene nanoplatelets suspended in sheared liquids.
So, thank you, Ed. Can you all hear me?
Yeah.
That's perfect. Okay, so thank you very much. I'm very excited to be able to speak in front of this very distinguished audience who very evidently knows about MD much more than I do. So today I'm going to talk about graphene nanohydrodynamics. And the basic question that I'm trying to address is what is the behavior of graphene particles, graphene colloidal platelets that are suspended in a shear flow. So this is work that I've started when I was at Queen Mary University, and I recently moved to Delft in the Netherlands. So the people that are truly responsible for the work that I'm going to present today are Simon Gravel, who joined my group from the group of Lideric Bouquet. So Simon is the expert in non-equilibrium molecular dynamics. Catherine Kamal comes with a background in mathematics and continuum mechanics and was responsible for the theory and numerical simulations, and she's now in Cambridge. and my PhD student Adiant, who is taking on the job that was previously done by Catherine and Simon. So first of all, I would like to start with some definition, with some terminology. So what do I mean by graphene nanohydrodynamics? So the term colloidal microhydrodynamics was a term that was introduced in the 60s by George Bachelor, famous professor of fluid mechanics at the Damt in Cambridge, to really define a field of fluid mechanics that dealt with particulate suspensions and the relation between particulate properties and the macroscopic behavior of a suspension, particularly rheology. And it's a very sophisticated field in which theoretical and numerical solutions for the stresses around a single particle are used to extract properties for an entire suspension via averaging methods. So I consider colloidal nanohydrodynamics as the modern evolution of colloidal microhydrodynamics when we deal with objects that are nanoscopic, at least in one dimension. Importantly, I consider colloidal nanohydrodynamics as distinct from what people call nanofluidics, which is kind of an emanation of an evolution of the field of microfluidics, because we are talking about objects that are suspended in the fluid. So we are not talking about flow of liquids in stationary channels, but the particles can actually move in the three-dimensional space. So graphene, you may know that in many applications, graphene take the form of for particulate material. So they look like colloidal platelets of lateral size that ranges enormously from about 10 nanometers to about 10 microns. But the thickness is unambiguously very small. Graphene is essentially a single atom, monolayer of carbon atoms that is 1 atom thick. So there are many estimates of the thickness, but we are talking about always less than 1 nanometer. And it has a very smooth surface, and this has many implications. So why do we want to study the fluid mechanics of graphene? Well, because graphene is essentially used as an additive in many liquids in several applications. So if you suspend graphene in a liquid, then you can have a mixture that inherits many of the good properties of graphene in terms of mechanical properties, electrical properties, and so on. And you can use all the processing methods that are used for liquids, such as coating, spraying, and so on. You can create graphene inks that conduct electricity, fibers that have extraordinary mechanical properties, nanocomposites, and etc. So the applications are not futuristic, but are already finding applications in the current market. Just as an example, I brought this picture of the tire of my own road bike. So there is a company that's called Victoria who makes a compound of rubber with graphene, where graphene is essentially used to enhance the puncture protection of the tire. Besides application, there is also a very nice scientific driver, because by exploring the fluid mechanics of graphene, we are also exploring the fluid mechanics of the thinnest object that has been conceived by man. The project that I'm leading is called Flex Nanoflow, and has dealt with several different aspects of the fluid mechanics of graphene. And today I'm going to talk about orientational dynamics of graphene nanoplatelets in simple shear, and very briefly touch upon liquid phase exfoliation. The approach that is followed in my group is that of combining analytical theory with continuous simulations based particularly on the boundary integral method, which is a method that is extremely efficient and accurate for Stokes flow problems that are relevant to the type of scales that I'm interested in, and molecular dynamics. So I come with a background in theory and numerics in the continuum limit, and I do not claim to be an expert in molecular dynamics, particularly in front of the level of sophistication of this audience. For me, molecular dynamics is more a tool to start thinking about problems and develop a theory. So I will start with the flow-induced orientation because it's a topic that I dealt with for quite a long time. So many of you will know that if you suspend elongated particles, whether they are rods or platelets in a liquid, and you apply shear, then you say that the particles will align with the streamlines. Well, this is true, but it's not precise. So alignment of the particle is in an average sense, so in an ensemble average or time average sense. But if you look at what happens to the particle individually, well, each particle will rotate, performing a very particular rotational dynamics that was very well studied by Jeffrey at the beginning of the last century. So imagine that I take a particle and I suspend it in a simple shear flow that is here illustrated. Well, there is a vorticity vector that is associated with this shear flow that and the sense of the vorticity vector defines the sense of direction of rotation of a fluid particle that is suspended in the fluid, and in this case it will be clockwise. So now we take a particle and we suspend it in this fluid, and just by intuition one might imagine that if because of the friction at the flat faces of the particle, well, the particle will rotate clockwise. Well, this indeed is the case, and this was explained by Jeffrey through his theory, but through a dynamics that is not obvious. So if here in this simulation that I will hopefully enable, I don't know why I cannot see my, I cannot see it. Yeah, okay. Sometimes the pointer disappears from the screen, sorry. So in this simulation, I'm showing, why is this happening? I'm really sorry. Okay, let me see. So this is a binary integral simulation of a platelet suspended in the shear flow. And the rotational dynamics is as follows. So the particle spends most of the time with its long axis oriented along the streamlines. And then it flips with the larger rotational velocity when the particle is oriented perpendicular to the flow. So because the particle spends most of the time aligned, then in a time average sense, we can say that the particle is aligned with the streamlines. But instantaneously, the particle is rotating with the same sense of the vorticity vector. So I wanted to test this prediction and whether it applies to to graphene as a nanoparticle. And I have asked my postdoc Simon to carry out the first MD simulations of a graphene particle that is suspended in a simple shear flow. The techniques are quite standard, so we apply a shear through moving walls. The solvent here is water, and we initially stimulated the graphene bilayer, so 2 layers of carbon attached to each other. The shear rate is, of course, enormous, but the Becquerel number is still reasonable and physical, so a Becquerel number of about 100. Maybe the only element that you would want to know as a simulator is that in these initial simulations, the molecular field is truly three-dimensional, but the configuration of the particle is two-dimensional. So we take a particle that was width, spans entire width of the computational domain, and we use periodic boundary conditions at the lateral boundaries. So we are actually constraining the particle dynamics so that the rotational dynamics of the particle is in the flow gradient plane. So from these simulations, we noticed something that is very intriguing and that was initially very puzzling. So we see that the particle does not rotate, but instead attains a very specific orientation at a very particular angle, of course, with fluctuations around this angle due to Brownian motion. And we have spent really the last 3-4 years trying to get the grips of this very particular phenomenon. We have explored different parameters, and we have seen that this inclination angle for which the stable orientation is achieved is strongly dependent on the aspect ratio of the particle. So I will try to explain the physics, the microphysics of this phenomenon very quickly. So if we consider a classical colloidal platelet, we can extend the rotational dynamics of the particle by considering the torque on the particle when the particle is held fixed with its orientation along the streamlines. In this case, there are two components of the torque. One is due to the tangential traction, as friction acts on the basal plane of the particle, on the flat surface of the particle. And this gives rise to rotation that is clockwise in this illustration. But then there is another subtle component to the torque that is due to the normal traction, so to the normal forces that the solid exerts on the fluid or the fluid exerts on the solid by the action-reaction principle. So this component of the normal force is essentially due to the fact that in order for the streamlines to curve upward here, so to satisfy the no penetration condition, while the solid must exert an upward force on the fluid, and therefore the fluid exerts a downward force on the solid, and therefore the corresponding torque is as a counterclockwise direction of action. So you can see that these two torque components have opposite sign, and it just turns out that the first contribution to the torque is slightly, very slightly larger than the second contribution to the torque. Actually, to leading order, they cancel out identically, and only if you do an asymptotic analysis of the problem, because I do not have time to go into many details, but one can take the stress, express the stress in an asymptotic expansion in terms of the small thickness of the particle, insert this expansion in the boundary integral equations that govern the relation between forces and velocities, and get the stresses on the particle surface to various order. And this analysis tells us that the first contribution to the torque is slightly larger than the second contribution to the torque. The difference is extremely small and is of the order of b over a squared, where b is the thickness. So even a tiny, very, very small change to the boundary conditions can perturb this very, very small, very delicate torque balance. What can perturb the balance in our case? Well, we have look at the stress, the tangential stress from MD and compare it to the continuum simulation. And we have noticed that the stress is much smaller than what we expected initially from a simple product between the viscosity and the shear rate. And the reason for this is probably obvious to this audience, and the reason is slip. So the graphene tend to have a very large slip, particularly with water. We measure slip lengths of about 60 nanometers for the force fields that we have used. And this is actually quite compatible with what was found in the literature by other authors with a variety of force fields and using different methods. So the effect of slip is to change the torque balance that we have examined before. So here I see the torque as a function of the declination angle of the particle. And you can see that for a no-slip platelet, the torque has always the same sign. And this corresponds to Jeffrey orbit, where the particle rotates always in the same direction. However, if we include slip, and this is typical of graphene, both monolayer and bilayer and tri-layer and so on, then the torque curve shifts upward. So there will be a value, a very specific value of the angle for which the torque is 0. And this is the angle at which the particle will attain a stable orientation. We have done an asymptotic analysis similar to the one that I described before. And this analysis suggested that the critical value of the slip length, which gives rise to a stable orientation, is of the order of the thickness of the particle. I think this is a very profound result, because it gives us insights into why people have not actually observed this phenomenon before, or at least why they haven't noticed. Well, the classical field of colloidal hydrodynamics deals with plate-like particles or rod-like particles, for which the thickness might be very small, but is always or almost always larger than the slip length. Instead, by examining graphene, we have just examined the opposite case of a particle that is much smaller than a typical slip length, even if you consider graphene particles that are made by several layers. With a thickness of 0.3 nanometer, you can easily imagine that you need a very large thickness in order to reach a slip length of 60 nanometers. This Teams connection is not working properly on my side. You hear me?
Yes. But I think the slide might be stuck.
Yeah. Let me try to stop sharing and share again. I'm really sorry for this. I don't know what's going on. So we believe the results are actually quite robust, and they are not limited to graphene and water. Indeed, graphene has been proven through many studies to have a relatively large slip length with a variety of solvents, including solvents that are very useful for practical applications such as LNP. And it may not even be limited to graphene itself. Indeed, the theory that we have developed is based on a continuum, point of view, and therefore the criterion that we have found is universal. Many 2D nanomaterial not made of carbon have also significant slip length. The slip length is typically of a few nanometers, but this is typical. This is still much larger than the thickness of the particle, and therefore we should observe such dynamics. Unfortunately, the experiments are not yet available, and this is mostly due to the fact that graphene is quite a dirty object to play with, and a typical graphene dispersion is extremely polydispersed. So just measuring properties of such system as leads to having to deal with the stochastic nature of the suspension. So we have also examined other effects such as Brownian motion. Clearly, the effect of Brownian motion is to randomize the orientation of microstructure, so there will be a critical value of the Peclet number below which an orientation is not observed. We have identified an intermediate value of the Peclet number for which the particle stays on a stable orientation, but through rare event it jumps out of this what we call hydrodynamic potential well. So macroscopically, what you see is that the particle does rotate, but with a frequency of rotation that is much smaller than what would be predicted by using a no-slip platelet. We have also examined the effect of flexibility and found that the theory holds true. So the behavior, this characteristic behavior of attaining a stable orientation holds true also for a relatively flexible particle. And this is really due to a very lucky combination of events. So the particle orients at a positive orientation angle, which means that the particle is it tends to orient nearly aligned with the extensional axis of the flow. Therefore, even in cases where the particle is flexible, the particle is being continuously stretched by the extensional forces due to the flow. Therefore, even if the particle is flexible, it does not tend to buckle, because typically when if you put a flexible particle in a flow, it tends to buckle when the particle reaches the compressional axis. But fortunately, because of slip, the particle never reaches the compressional axis and stays stably in the extensional range of the simple shear flow. When I showed these results to several years ago, when I still was in Queen Mary, I had the opportunity to present my result to Jean-Marie Leng, who is next Nobel Prize, still Nobel Prize winner in chemistry, and he suggested to look beyond graphene, and he said, why don't you actually look at the general flat macromolecules that have a geometry similar to graphene, and they are made of carbon. There are plenty of those, and they are called polycyclic aromatic hydrocarbons, and they are really the elemental constituents of all the hydrocarbon found in nature and technology. In recent simulations, we have looked at hexabenzochroning, which is essentially a molecule that looks very much like graphene. It's just much smaller, and it has hydrogen atoms, lining the outer edge of the particle. And we have carried out simulations of this molecule. And so these are truly three-dimensional simulations. So we have a three-dimensional disk, which is also, free to move out of the plane of the flow. So here we have truly not constrained the dynamics of the particle. We found a very good agreement at the qualitative level, qualitative level and semi-quantitative level between our theory, which is semi-2D, and the simulations. One of the interesting things that we could do with the simulations is to measure the viscosity, and in particular the excess viscosity that is due to the particle. So if you put particle in the fluid, typically the suspension goes up, and we can measure the excess viscosity, which is called the specific viscosity. And I found that because of this alignment of the particle nearly aligned towards the streamlines, the undisturbed streamlines, then the viscosity, the specific viscosity drops by a large factor, by about 300–400%. So a very significant effect that is due both to a reduction in friction on the particle surface, but also to the fact that a particle that is stably aligned disturbs the flow much less than if the particle was continuously rotating in an average sense. The practical implications of this work, we believe, are mostly in the area of lubrication. So graphene is already being used in research related to additives for various organic and aqueous lubricants, where one wants to exploit the superior chemical and thermal stability of carbon nanomaterials to impart new properties to the suspending fluid. And our results may suggest that one can, if you design the graphene colloids appropriately, one can still obtain benefit from the addition of graphene to the liquid without incurring in the penalty of an exceedingly large viscosity of the entire suspension and entire lubricant. Another thing that we have examined is delamination by shear flow. So what happens when the particle, a multi-layer of graphene particles that are held together by relatively weak van der Waals forces are separated by the shear flow. So when the hydrodynamic forces reach a critical value, then the layer will debond. And this has important implications for the so-called liquid phase exfoliation, which is one of the most scalable methods to produce graphene on large scales by starting from simple graphite. And we have developed a model that we believe is the first validated model for liquid phase exfoliation, and we have compared against MD data for a variety of solvents, and you can find details in this publication. We'll try to wrap up because I'm mindful of time. So in summary, we have seen that there is a very interesting physics to be explored when the slip length is comparable to the thickness. The work was really motivated by MD. Everything started from there, and the current work is trying to. In current work, we are trying to get grips, to completely understand an initial observation that is for us very puzzling. So when we started considering the excess viscosity of graphene in different solvents, we have also included NMP as a solvent. So NMP is particularly viscous, and we found a result that was extremely puzzling and still is. So we have found a value of the excess viscosity or specific viscosity which is negative. So the specific viscosity is just the difference between the suspension viscosity and the viscosity of the liquid normalized with the viscosity of the liquid. So a negative specific viscosity means that we have a suspension of particles in which the viscosity is less than the viscosity of the liquid. So this is truly, truly remarkable. conventional wisdom says that if you take a suspension, you put particle in it, then the dissipation must go up. And the reason is that the particle will disturb the flow, and therefore the excess dissipation due to this disturbance is seen as an excess viscosity. What we have found is that there are situations for which this is not true. And it seems that the graphene is the only particle, or the particle that has the right geometry and the right slip properties, that gives rise to a negative specific viscosity. I've currently asked my PhD student to do more careful studies of this phenomenon. He has found that there is a critical value of the Peclet number and a critical value of the aspect ratio of the particle beyond which one can obtain a negative specific viscosity. I believe the result is actually physical because the viscosity is just a measure of the friction between fluid layers. Now, if you can imagine that you can replace one of these fluid layers with a solid particle, and if this solid particle has a reduced friction with the other liquid layers, it is perfectly conceivable that the entire system has a reduced friction to sliding, a reduced resistance to sliding. The key property that the system must have is that the particle must always be nearly aligned with the streamlines and do that instantaneously. And it seems that our graphene particles of the system that we are studying have exactly this property. So they have large slip and they maintain an orientation that is instantaneously almost parallel to the streamlines. So with this, I would like to conclude, and I would like to thank my collaborators and the funding agencies. And well, I will be very happy to take any question. Thank you.
Perfect. Thank you very much for a very interesting talk. So do we have any questions? Please, David.
Yes, very interesting talk. What factors affect the alignment, the angle of alignment? Does it vary with shear rate, for example? When you increase the shear rate, does it change that angle?
So based on our continuum analysis, which is both theoretical and numerical, and is based on continuum theory fitted to the MD results to get the parameters, we find that the angle depends on the square root of the aspect ratio, where the aspect ratio we define it as the thickness divided by the length. So if longer particles will have a smaller inclination angle. And this has interesting implications for graphene because the aspect ratio, the length divided by the thickness for a graphene particle is typically of the order of 1,000. For graphene oxide can be up to 10,000. So which means that in practice, a relatively large graphene particle will be macroscopically instantaneously aligned with the streamlines.
Have you looked at needle-shaped particles, like rods, for example? Do they do the same thing?
We didn't do a complete study, but I expect that you will not see the same effect. And the reason is that difficult to explain, but essentially the mechanics of rotation for rods is different from the mechanics of rotation for plates, even though quantitatively there are many symmetries and analogies. So for instance, this I told you that there is this dominant contribution to the torque that comes from the friction at the flat face of the particle, and that scales like the viscosity times the shear rate. Well, that is actually not true for a rod-like particle, because you can imagine that you cannot just if you want to calculate the torque, you cannot just take, the length and multiply by the thickness and multiply by the shear rate and get the force on the top part of the cylinder. So indeed, actually, this is a study that I would like at some point to delve more into, but based on the on the theoretical treatment, I do not see a reason for a stable orientation to emerge also for cylinders.
I know in the classical theories for needles, you can get this effect called kayaking, where it oscillates, the angle oscillates with time. That would be interesting to see if you could get that. With
so the kayaking is a description of this very famous Jeffreys theory that was derived for no slip particles, and so our particles kayak mostly because of the thermal fluctuations, but we don't actually see the same type of dynamics predicted by Jeffrey, not even qualitatively. And because we are actually, we are truly challenging Jeffrey's theory when applied to particles that have nanometric thickness. The theory is exact. Jeffrey's theory is exact, but one of the basic assumption of the theory is perfect no slip.
Yeah. Okay. Thank you very much.
Thank you very much. So if we can thank our speaker again, and we move on to our last talk for this session, and that's Sergey Karabasov on a thermostat-consistent, fully coupled MD generalized fluctuating hydrodynamic model for non-equilibrium flows.
Thank you very much, Ed, and let me share the presentation. I hope it works. That's one.
Perfect. You can see.
Let me go to the full screen. Yeah, that's the full screen it should be. Right, so first of all, thank you very much, Ed, for including my talk at the very last moment. And thanks for those who are staying around, because it's already more than 5 o'clock, and it has been a very long day today. So yeah, so this is a talk where I'm going to discuss the latest developments in our multi-scale method developed some years ago, and the two main co-authors in this work are Xinjian Liu and Ivan Korotkin. Xinjian is a visiting PhD student with me, and Ivan now is a postdoctoral associate in Southampton. Also, I would like to acknowledge cell colleagues such as Dmitry Neruch at Aston University, Vladimir Farafonov from Ukraine, and a couple of my PhD students, Fan Li and Jinggu Hui, as well as my colleague Anton Mackenstein, who now works with me on a different project. And over the years, this activity has been supported by several bodies such as the PSRC, European Commission, as well as Chinese science scholarship. Right. So what this is all about is that we're interested in modeling of situations when, in addition to the macroscopic or the bulk volume of the flow, there is a confinement region in the flow where the continuum laws typically break down, and applications which, well, of course, today you've seen multiple applications, but a few more to the list is the modeling, for example, of forces which occur in a small gap between the atomic force macroscope cantilever and a material substrate. What happens with the forces if you have also a water layer there, and also what happens if you're trying to sort molecules in a small nanoscale device under the effect of shear and pressure gradients. Well, in this case, clearly the continuum approaches such as Navier-Stokes are not sufficient, and this emphasizes the need for concurrent multi-scale models, which where you ideally should couple continuum approaches such as computational fluid dynamics with molecular dynamics. So in a way, if you think about the parameter space, somehow you should be treating the large scales which are resolved by CFD or continuum models, and small scales which are resolved in a molecular dynamics as some boxes in this parameter space, and you should organize the exchange of information, well, in the conventional multi-scale framework. Of course, this balance between the large scales and the small scales is delicate, because typically high resolution method, which is molecular dynamics here, although it's is first principle, but it's costly, whereas continuum fluid dynamics, you can do lots of simulation with it, but it's you will need to acknowledge that there is a certain limit of applicability of this model. And the way we would like to look at this problem as at the problem of setting up boundary conditions for molecular dynamics simulation, because by its nature, molecular dynamics is very expensive. So you would like to actually only do this calculation where it's really needed, which is typically in a small domain. Hence, if you want to couple this with continuum flow simulation effectively, you can think of using this continuum flow simulation as some boundary condition. Well, this boundary condition can be considered as a non-local boundary condition, because of course in comparison with the continuum methods, particles have a certain range of interaction. Hence, you cannot really just cut the domain in two and specify completely two different models. So therefore, you need to explain what happens in some part of the domain of dependency of a certain particle, which is close to this interface where there is no particle. This is where the question mark is put here. Now, the way we tackle this problem, actually, we've come up with the method called two-phase flow analogy. And the way it works is that you can think of a homogeneous liquid, which actually can have some heterogeneities at atomistic scale, as of a bulk, as of an effective bulk two-phase liquid, which where the phases are the continuum representation of the same liquid, and the atomistic representation of the same. That is, in, let's say, if we introduce a concentration function, then the partial volume, which is occupied by the continuum part of the system, we can call it S, and then the rest, which is occupied by discrete particles, is 1 minus S, because there are some should be equal to 1. So then you can formulate the equation for the conservation of mass or concentration and conservation of momentum using the classical two-phase flow liquids. And you would have something like is written here. So the change of mass plus the divergence of all the fluxes. Mass fluxes in this case is equal to some sources which appear because you can allow actually the second phase to transfer to the first phase. So that's sources which you can have in mixable phases. Of course, in the case of the continuum phase, you can think of some differentials or some continuum formulation. In the case of the particle phase, when you have discrete particles, you have to do a summation of the discrete particles over the control volume. But the nature of the conservation law stays the same. And what's important is that when you add up those two conservation laws together, the source and sink on the right-hand side will cancel out, and then you will have the conservation of mass. The same will actually happen when you write the same equation for the momentum. So hence this approach of explicitly introducing the two phases which represent the same liquid allow you to exactly preserve the conservation of mass and momentum. We haven't done the same with the energy so far. And those source terms J can be defined in accordance with how fast you want those two phases to mix one with another. Now the parameter S is actually the user-defined parameter, and this is what you can define in the volume to specify which part of your chemistry domain is occupied by the pure molecular dynamics and which part is occupied by the particles which are driven by the continuum equations. And just to mention that those source and sink parameters J, they can be adjusted to correspond to the optimum transfer of the mass and momentum from the continuum phase to the discrete phase and vice versa. And consistently, the same modification has to be done for the particle equation. So instead of classical molecular dynamics equations, you will need to solve some equations of which are similar to the second law of Newton, plus some external forces due to the hydrodynamics. We'll talk about this later a little bit. Now, the next question is, how do we solve those equations even for the continuum part? Well, the most effective way to solve the system of two-phase equations is to reduce actually to the equivalent single-phase flow equations, and that can be done. So instead of in comparison with the classical fluctuating hydrodynamics Landau-Lifshitz equations, which is on the left-hand side, so you can see that we have here mass and momentum equation with some viscous stresses and the fluctuating component. On the right, these are the modified equations which we derived back in 2018 for the two-phase flow analogy. Rho star and the Q are the effective density and momentum, where on the right hand side we have some sources which are coming from the interaction with molecular dynamics. And the last two equations, which are the rho prime and Q prime, are the differences between the continuum phase and the molecular dynamic phase. Now, the important property of these equations, which we called generalized Landau-Lifshitz fluctuating hydrodynamics equations, is that in the limit when the S is equal to 1, this system of generalized Landau-Lifshitz equations reduces to the standard classical fluctuating hydrodynamics, and in the limit of S equals 0, so this is pure MD region, actually we're reconstructing the exact balance which you can calculate from molecular dynamic solution. So that's a very big difference in comparison with the classical Landau-Lifshitz model, which is only statistically equivalent to the molecular dynamics. The generalized model actually is exactly the same as molecular dynamics averaged over control volume. Now, back in 2018, we've done some tests for the liquid argon, and the idea and the model which we built at the time was to put a box filled with particles where we have a variable C solution. I'll put an animation for the particles too. So the red in the center corresponds to the pure molecular dynamics. The blue in the corners corresponds to the hybrid domain, where S is close to 1, where the particles are driven by the hydrodynamics. Those particles can swap from one side to another via the periodic boundary conditions, because those particles are not quite atoms already. They're almost like hydrodynamic particles. It's much easier to impose the periodic boundary conditions there. And the rest of the domain, where there are there are no particles, we are solving the continuum flow equations in accordance with the generalized Landau-Lifshitz. And of course, the number of control volumes can be quite small there, so therefore we can expand the boundaries of this domain over a pretty large domain. So we've done the test for this, for the Lennard-Jones potential in the past, such as quiet flow and acoustic wave propagation, all works. And then, okay, the next question was, how do we actually extend this for more interesting and useful systems such as water? And one of our favorite water models is SPCE. The problem with the water is that in comparison with Lennard-Jones, which were monatomic substances like argon, here we have a molecule and we have additional degrees of rhythm, and as well as we have long-range interactions, which we need to treat accordingly. So therefore, the interaction between the individual atoms of water are much stiffer in comparison with the argon, and typically, of course, when doing molecular dynamics simulation of water in a sufficiently large ensemble, we need to apply some thermostat to account for the unbalanced energy of the system. There are different options. One of the simplest options is due to the, well, is Langevin thermostat. It's simple, like I said, but the problem with this thermostat could be that it doesn't conserve the linear momentum in comparison with some other thermostat. Now, it's all fine when you are doing the pure molecular dynamics simulation, but once you start introducing the additional phase, i.e. the hydrodynamic, you will need to distinguish between the effect of the particles and the effect of the hydrodynamic phase, which is not which is incorporated by the effective forces. So hence what we had to do at the time is to adjust the thermostat equations, such as, instead of calculating the temperature as the standard summation of the squares of the velocity in accordance with the equipartitioning theorem, we introduced a model equation based on some effective total enthalpy. So when we are essentially adding the energy of the particles and the energy of the continuum with some weights in accordance with the concentration. I'll probably go faster now and say that it turns out to be that this weighting, which we need to incorporate in the local thermostat equation, cannot be just defined based on the geometrical factor. In fact, the particles have a certain inertia, and therefore actually they tend to occupy a bigger volume than you would expect just from the concentration field. And that was published back in 2020. And we had some good results both for the radial distribution function and for capturing the correct local temperature in the pure molecular dynamic zone. You can see that the distribution of the particle temperature follows some parabola where the peak corresponds to the pure atomistic region, and then the branches are decaying because here we have an unaccounted contribution of the hydrodynamics. So here is just showing the particle temperature. Now the problem now, well, the next problem which we had to solve now when we want to apply this for the real non-equilibrium situation is that, well, adding the flow to the molecular dynamics model can actually violate the property of the thermostat, which is which so far we have been using Langevin, and that is based on the thermostat does not conserve the linear momentum. So what we've done there to calculate the Poiseuille flow, we've separated the our solution into the time average mean plus the fluctuation, and then we solve the fluctuating hydrodynamics equations for the fluctuation only. And then, of course, we needed to organize the information transfer from the continuum generalized Landauer's equations to the molecular dynamics and then back. So we see that, and once this was done, we first of all made sure that we can capture the analytical velocity profile well in comparison with the analytical solution. And on the way, we found that actually there is a sensitivity to how we approximate the long-range interactions. From the literature, we know that there are different methods, and one of the rudest methods is based on the cutoff, whereas the reaction field is more recommended, as well as PME. And what we find is indeed that the reaction field appears to work better for preserving the profile of the mean averaged low velocity of MD particles inside the pure MD region. We've looked also at the fluctuation of the density and velocity, and we find that it all converges to what we expected. The final thing which we've done was to compare not just the temperature, which was captured by the local thermostat, but also the density. And this is where actually we saw quite a significant difference between the cutoff method and the reaction field. We actually see that the density is not preserved, and hence the pressure is not preserved when we're using the simple cutoff method. In the molecular dynamics simulation, we were using NVT, so hence pressure will not guaranteed. So hence we needed to do some extra work to also capture the pressure. So that's probably the one of the finalist slides, where we're comparing the RDF function, the radial distribution function of our model based on different electrostatic force field models in comparison with the reference or atom molecular dynamics. And we can see that indeed the reaction field works much better. Hence it is recommended as expected. And one more important comment here is that, of course, multi-scale methods are typically more involved in terms of the implementation. So why would we need to use them instead of the non-equilibrium molecular dynamics, for example? But what we can see that in comparison with the standard classical MD water simulations in the same Tomax version, we can have up to 20 speed up depending on the domain size. So that's because we can, of course, select a much smaller molecular dynamics domain in comparison with the overall domain where we're interested to calculate the bulk flow. So this is one of the first times when we actually show the actual speed up in comparison with the pure molecular dynamics with our method. So these are the conclusions. You can read them, but just to say that so now we have a working and robust two-way coupled model which is implemented in GROMACS, which can calculate non-homogeneous flows and also capture the important microscopic information. The code is available on the GitHub, so if someone is interested in playing with this modified GROMACS version, they're more than welcome. Thank you.
Thank you very much. So, do we have any questions? Oh, a bit of an echo.
Tired.
That's better. Okay, so I know there are a couple of questions from before. I think Philip Camp and Maxim were going to ask Dimitrios a question. So this discussion session, we're actually quite a bit over now. So, I mean, for the rest of today, I've basically only got about 15 minutes left, where I'm just going to finish off and just present to you about the Snook Prize, which was Bill Hoover asked me to present basically a few details of that. So that's the last thing I want to do today. So we maybe take a 10 minutes for either for discussion or just for a quick break, and then come back maybe at 45. And obviously anyone has any questions, feel free to discuss now, but I will start again just on the last 15 minutes at 5:45, and then we finish at 6 o'clock today.
Sounds
so
good.
Yeah,
also, maybe if I can propose, we can also use the chat.
Okay, so I mean, if we have no discussions, I'm just going to ask just as a question about your methodology. So it's kind of a blending function. If I understood correctly, the thermostating then introduces an energy constraint. Is that correct, or?
Yes. So the idea is that thermostat is done in molecular dynamics anyway, and what we do with our methods, we introduce an energy constraint effectively using the hydrodynamics. So this idea of consistent thermostating follows from the fact that we need to make the two consistent. So whatever you do with your standard molecular dynamics thermostat needs to be consistent with what you do with your equations. So we should not. It probably goes back to the first talk today, that when you are over constraining your system, it becomes very stiff, and then it will not be stable, perhaps. So we should not over constrain our system, and this is what we're doing by applying the local thermostat.
Yeah, that makes sense. The other thing with these coupling schemes is, I mean, there's definitely in the coupled literature, there's an effort to take the energy back out that the coupling adds in, and I've always had a sense that the energy should be added in. You know, your continuum should be doing work on the particle system, so it's not clear, you know, how much energy you should be taking back out again. You know, I think you probably have to solve the full energy equation as well.
Yes, right. So far we've done it for the either thermal fluids. So this is where the continuum energy is not not an issue. So we cannot, for instance, use it for combustion. So for either thermal liquids, we don't have a separate equation for energy. So hence, on the microscopic scale, we're dealing with the thermostat. But then our main concern, I guess, is more on conservation of mass and momentum, as well as the microscopic properties.
Yeah. I mean, it makes sense. I mean, the thermostats are well developed, whereas the others are less so. Do we have any other questions at all, Sergey? Or yes, please, David.
What actually was the thermostat? Was it a velocity rescaling?
It was not velocity rescaling. It was Jagjeevan thermostat.
Right. The Nose Hoover has a sort of feedback. It can put energy in as well as take it out.
Yes, Nose Hoover would be our next step. It's a little bit more complicated to implement, but yeah, as well as DPD perhaps.
Yeah, that's right.
Yeah.
Because I think, yeah, otherwise it could be too stiff, as you said.
Yeah, I think, excuse me, I think the DPD would be a really good idea, because with the Jagjeevan you don't have momentum conservation, whereas DPD is, I like to think of it as a Jagjeevan with momentum conservation, right? So it's, I think it's it's really. Yeah. I've also seen papers where they have multi-hybrids, so they start with MD and then they have some sort of layer in between.
Well, this is address, triple scale. The problem with this is that, well, when you stop with the complexity, that's the question. So if you have too many layers, then you have too many parameters.
Yeah, I agree.
And then the next question, which is also linked to this, is how do you make sure that your model is actually faster in comparison with the more simple perhaps model? This is a question which typically people don't often answer.
No.
Okay. So as promised, there was also a few questions. So I think for Dimitrios Mathas, there was a question from Maxim and Philip Camp, or at least they had their hands up way back when. I don't know if those questions are still, if they can even remember those questions, but in case they're still relevant, please.
Hi, no, I was really just going to comment on Carl's comment about using all of the components of the stress tensor either with Green Kubo or Einstein approaches. So we tried that, and it wasn't enough to rescue the those methods at very high pressure. So that's all I was going to say.
Did it improve it by? I mean, you'd think it'd improve it by, I guess. It should be twice as good, right? If you're getting 3 more components.
It should be, but it doesn't make any practical difference. Not at these very high pressures.
Isn't the pressure tensor symmetric though about the diagonal?
No, that's not the point. You can actually use the diagonal parts as well. So yeah, so it's more than 3. It's more than 3 components. So you can use 6. The 6 unique.
I think 5 actually. I was looking at this recently. I thought it was 6, but then it actually is 5. There's only 5 unique ones.
Yeah. So there was an interesting paper by I think it was Berend Smit, a short paper in JChem Phys a few years ago, where they were comparing all of these, well, at least the equilibrium methods. And so if you just follow their prescription, which of course is just lifted from Davis and Todd, it, I mean, again, at these extreme conditions, it didn't make much difference.
No.
Maxim, did you had a question?
Well, I had maybe quite naive question. So Green Kubo was used. In Green Kubo, I believe you need to put stress tensor at 2 different points and average over one of the points. Or maybe because the stress is defined only where particle is, you are forced to average over both points. Otherwise, I mean, it's either 0 or it's only located at particle. So I mean, I wonder how you deal with the fact that this forces only can be computed at particle locations, not everywhere. And also I was a bit surprised that even after ensemble averaging, this correlation function looks like an envelope of something very oscillating. So I was wondering, is it really should behave like an envelope of what is shown, or is it really oscillating that much? I was a bit surprised, but maybe I'm naive about this. Is our speaker around?
Dimitrios, did you hear? Are you?
I'm not sure about the question, but there are some. It has been seen in literature from some other papers as well that at higher pressures the EMD has issues with the autocorrelation function, and we have it doesn't decay to 0, so that's why we underpredict viscosity.
But is it oscillating even after ensemble averaging?
Sorry,
is it going through 0 very often after ensemble averaging?
The fluctuation of the autocorrelation function.
Yeah, you show the graph, and the graph looks like a decaying envelope, but inside the envelope it was going through 0.
Yes, this was an example of benzene, which was at atmospheric pressure, and the autocorrelation function, for this case, it did go to 0, but that was atmospheric pressure. But when we are at very high pressures, then the average fluctuation is not is actually higher. It's maybe 3 orders higher. I didn't show the high pressures autocorrelation function. I just showed I could share the screen, but if you want, but it was just one example. That the function I showed, it did decay to 0.
I see. Well, I am saying not about this long-term behavior. I'm talking about short-term behavior of this function. So it oscillates like crazy, and then it decays to 0 as an envelope. So does it have to oscillate at high frequency?
So in the beginning, yeah, let me show the graph. Let me share the screen.
Yeah, I mean, maybe I should.
So
Yeah, I mean, that's what it's doing. This is oscillating like crazy. And this is after ensemble averaging, presumably, which is a bit surprising. I mean, I would expect it just, you know, I would expect an envelope of what you're saying. Like, it is like, presumably, so it's not positive, you're saying. If I compute it as written, so it depends on this time tau. So at small tau, it's not like positive, it's like doing crazy stuff. It's oscillating as a function of tau.
Correlation at the beginning, because we correlate the function by itself, it's always 1 at the beginning. But then the pressure fluctuates from minus, let's say minus, I remember, I think for the low pressure, it's we have an average value of 1 atmosphere, but it fluctuates from minus 1000 to 1000, and that's why the negative correlation. But we take the integral of the function, and there are some empirical models that fit this function and can only have a positive value. But there are other papers in literature that show the exact behavior.
I see. Well, it's interesting. Maybe we chat later about it. But what do you do about the point at which you compute those stresses? I mean, it depends on the spatial point, which is suppressed in your formula. So at which spatial points you are taking those stresses?
So basically, at every time step, every 1 femtosecond, we have the value of the pressure tensor of the stress, the elements, and
they depend on the spatial point. So they are equal to something at where the particle is, and they're equal to 0 when there is no particle in there.
I'm not sure I understand, but pressure is calculated by.
It's like pressure in the whole domain.
It's the whole. It's the pressure is in the simulation. Pressure is calculated. The elements are calculated for all their average for all of the atoms. So it's the equation, which I haven't shown it here.
So it's like average pressure, average to all particles, is it not?
It's average at its for the particles, and this is calculated every femtosecond. And the pressure tensor has 2 terms: a virial term and an energy term.
Oh, so it's computed from the viral theorem, not as actual force on a surface. You use viral theorem to compute it.
Yes, I think yes. I have the equation.
I see, but if you use viral, it's probably it involves volume integral, so it's like some sort of averaged. Well, you know, we had a talk about this, another talk about this. We were discussing what does it mean a pressure at a point. So it's like similar kind of question. What is stress tensor at a point, or is it averaged over volume and stuff like that? So if you're using viral theorem, you're probably averaging it over volume in some sense.
Lumps in that case, it's average.
Oh, so you allow lumps to do it for you?
Yes, lumps does it for us.
I see.
We store the value in a separate file, and then with our in-house code, we perform different autocorrelation. We run different autocorrelation parameters, and we did a study to have converged the results as much as possible.
I see. What you can do alternatively, you can ask lumps to throw for you forces at each particle position, and then do something with those forces.
Yes, you can save the force. You can save the forces. That's possible.
I see.
Okay, so I think I mean, so in terms of conversation, there's no reason why we have to stop at 6. If people can stay around if they want to keep chatting. I just wanted to finish off with just a quick. It's only about 15 minutes. I'll try to do it quickly. Just on the Snook Prize. So let me just finish with this, and then I'll kind of close for the day. But as I say, we can feel free to stay around. So, I mean, firstly, just to say thank you very much to everyone for attending, to all the speakers, anyone who's still here at least. I'm very aware that a lot of people had to pick up children, or, you know, it's getting late. So I think we've lost a few people, but thank you very much to Matthew and James for their help organising. I think with the exception of, you know, a few dodgy connections, it went okay. Obviously, it'd be nice to meet in person, but, you know, we had talks from America and Australia and across Europe. So, sorry, India, China. So we've had goods and bads. So hopefully you found it interesting. All of the talks will be recorded, and I'll put them online. Computer's just slowed down. Yeah, so just a quick note, please sign up to the UK Fluids Network for future announcement, and this will be used for future meetings. I mean, certainly this is meant to be a UK-based consortium, but, you know, I don't see any reason why we don't make this international. I think it's essentially just a mailing list, and we can consider a conference. You know, please let me know if you're interested in hosting, or if you have funding available. I think for, you know, a few £1,000 and, you know, a bit of organisation, you can pretty much have an event. So yeah, so any questions or any comments at all on today? I mean, basically, I think you know, we'll aim to do another one in maybe a year or two, depending on organisation. And as I say, please let me know, get by email if you want to organise. Okay, so
thank you, Ed, and all the rest of you guys organising it. I think it was really nice to get a chance to meet everyone and to hear some fantastic talks, and it's really nice to see what's happening around in the different groups. So once again, thanks a lot for organising. I know just how busy everyone is these days, so I think it's important that we you know, keep having these meetings. So yeah, well,
thank you again for giving a talk, and to all the speakers. I think
my pleasure.
You know, it's been quite easy. Everyone made it quite easy to organise. Really, people just got back, and yeah, we managed to put it together. So let's do it again. So let me just finish with this. So I originally tried to rope Bill Hoover into giving a talk. You know, I thought it'd be quite a nice end to the day. I don't know if anyone's worked with him, but he's absolutely incredible. You know, he basically seems to work sort of every second of the day. You get kind of emails, you know, at sort of 4 a.m. from him. But I don't think he likes online talks. So he basically wrote up a lot of work, and I've spent the last kind of month trying to understand it so I can present on his behalf. So that's the background. The reason for doing it is because it kind of motivates the Ian Snook Prize. So for anyone who doesn't know about this, it's a prize offered every year. It's $1,000, and obviously the prestige of having an award. It's offered by Bill and Carol Hoover, but the other $500 of the 1,000 is put up by the Poznan Supercomputing Center, and its entries are in the form of journal submissions to CMST. So if you want more information, you can either click on, if you go to the website, you can click on a Snook Prize link here. You can search for it, or there's a link here that will take you directly to it. So part of the problem, I think, at least for me, is that this has become, you know, more abstract each year because it's kind of building on an idea. So what I'm going to try and do today is just give you enough background you can at least understand the problem. So the prize is for the information dimension of a 2-dimensional Baker map. So it's stated as the fractal information dimension can be commuted in 3 ways: mapping points, mapping regions, or applying the Kaplan-York conjecture. And for the simplest non-equilibrium Baker N2 map, these 3 approaches can give different results. And so the prize is for anyone who can kind of provide some clarity on this situation. So what I'm going to do over the next, hopefully, I'll try and make it not more than about 5 or 10 minutes, is just to give you an idea of what that's got to do with all of the talks we've seen today and NEMD, and then also really try to state the essence of the problem as I understand it. Now, I'll caveat this by saying that I'm playing catch up, and there's an actual archive paper written by Bill Hoover, which I should suggest, and sorry, Carol Hoover as well, that I suggest you look at to get a better idea. But, you know, from my point of view, I see it like this. We have, so I'm not sure I get rid of the bottom, but let's try again. Okay, fine. So the idea of NEMD, is we have these equations that are molecular equations. Conservation of mass is just how many particles you've got, Newton's law. Energy, you've got some Hamiltonian, maybe not equal to 0, but in principle, for systems without external fields, they are. And then entropy, which you can define at the molecular scale. Now, what we've talked about today has really been draw a grid over that, and then on average, you get the same behavior as the mass, momentum, energy, and again, entropy is less clearly connected. But I think Sergey still really kind of showed this kind of more explicitly. But basically, we have the same equations. We can average them. We get these kind of larger scale. However, one thing we haven't talked too much about, and this for me is where NEMD has a real strength, this non-equilibrium molecular dynamics, is we have this basis in statistical mechanics. So rather than talking about kind of averages of particles, we can talk about flow in phase space. And you can think of these as kind of an average of the positions and momentum of the particles, or the state of the particles. And it's a kind of more fundamental equation. So the volume in phase space is incompressible, which is a similar statement to the kind of density continuity equation in fluid dynamics, but in this phase space. So this is a plot of, say, all of the positions and all of the momentum of a particle. These volumes are incompressible. So this is a kind of more fundamental description. And conservation of energy, or conservation of a Hamiltonian, is a kind of a stricter version of this. This is a kind of more general form of how the dynamics should progress in a molecular system. And this concept kind of underpins lots of our stat mech. So if you go to the paper by Irvin and Kirkwood, where they define the stress tensor everyone uses, notably not lamps, as we've been saying, because it uses the wrong form, you get essentially the underpinnings of this derived from Liouville's equation. Things like entropy can be derived by fluctuation theorem. The viscosity, the Green-Kubo relations come from this underlying theory, kind of perturbed. And things like surface tension, again, will be derived based on this statistical mechanics phase space framework. So this for me is the kind of backbone of NEMD. So just to give you a kind of tangible example of this, if it seems a bit abstract, you can think of a simple harmonic oscillator. So we've set all of the coefficients to 1, and you can see this as a Q dot P dot form of just equal to P and Q. And so you get this cycle where it just oscillates up and down, and you can plot this in phase space. So for example, when it's maximum compression, the position would be 1, for example, here, and the momentum would be 0. So it's not moving, it's as compressed as possible. It uncompresses, at the point of kind of maximum momentum. Its position is 0, and its momentum is say -1, moving down, and it goes around in this cycle. So you can think of the simplest possible example of this, this kind of conservation of energy, or this interchange of momentum and position, giving a constant volume in phase space. So when we talk about phase space conservation, we see this constant area in phase space, and this is the idea of a conservative system. However, if you build in a Nose-Hoover thermostat into that system, you can start to get some very complicated behaviors. Now, this is actually shown here for a harmonic potential, but you can get, I think you have to go to a non-harmonic to start to see these kind of chaotic maps. But, essentially you stop seeing this kind of conserved phase space, and you start to see this kind of multi-fractal and really complex phase space, as well as these unstable orbits, and then a whole range of very, very complicated physics that I would say is linked to kind of viscosity, entropy, possibly turbulence, as well as some of the kind of non-linearities we've talked about today. So as a problem, this is linked to that. And so the Baker map we finally come to is basically a simplified version of that. So you can think of it as a QP space. There's a Q just off the page here. And it's essentially a mapping. So rather than just having the harmonic oscillator we have here, that's the evolution of Q and P, it's essentially just a mapping. But it gives you the same essential dynamics of phase space being evolved in some way. So you can see here, this is what this mapping does. If it goes above this line, it gets mapped down. And if it's below the line, it gets mapped up. And you can think of this as kind of a phase space described by a kind of toy model. So it's a nice way of really getting to grips and understanding the essence of phase space. And if you look at the paper, it will explain in more detail exactly what this does, but the actual the mapping is quite straightforward. So what we can show is that shrinking phase space volume and this kind of phase space becoming fractal is actually what gives you the time irreversibility. So this gives you entropy, and this gives you this kind of non-reversible behavior. So despite having a time reversible Baker map, in the same way we have time reversible molecular equations, we still end up with kind of these solutions which are increasing in entropy. So this toy model basically just halves the white area or doubles the red area. And you can think of this as being a kind of a picture, but really what we do in the actual code is just take a single point and you evolve it like a particle. So it's essentially like a dynamic equation involving that particle. And despite having a kind of compressive on average system, we see this loss of phase space volume. You also see chaotic behavior. So you'll see trajectory divergence, even if you go to say 128-bit, after about 40 seconds, you see these trajectories diverging. And you can show things like the Lyapunov exponent matches quite well with the expected theoretical results. So it's a nice system. It's kind of, predictable, and it allows us to explore this phase space. So let's just quickly consider what we do. We take this phase space here and we plot basically all of the points. So if we look, we see essentially we get this kind of fractal distribution of points. So the phase space itself is becoming more fractal the longer we run it for. So what we can do is we can take that and we can bin it. So this is the same concept that we bin values to get, say, mass and momentum. We're binning this here to get the points in phase space for this simple system, and that gives us a kind of histogram in 2 dimensions. So you can think of this histogram in 2 dimensions, and we can map it to 1 dimension. You can see it's 1-dimensional along this kind of Q equals P line, or Q plus P is a constant line. So what that gives us essentially is this distribution of phase space. And so depending on how you bin it, you get a different fractal of phase space. So it's a simple model giving us this kind of multi-fractal behavior. So just a side note on another way we can get these behaviors. This is what's called the Baker map. You can actually use just a kind of random walk. So for anyone who likes the kind of Jagjeevan thermostat or stochastic equations, this is a kind of even simpler way of getting the same thing. So rather than doing the Baker mapping, you can just do exactly the same thing with a y coordinate of the same form, which is just a mapping, and then just a random number. So the concept's the same. You can use the QP, you can use the confined walk, both of which I think are valid for this particular Snook Prize problem. And so then what we do is we divide either of these maps into just a grid, and we're considering multiples of either 2 or 3 for the binning, and that gives us different fractal maps. Now, one thing you see for both the Baker map and the confined walk is they give identical fractal distributions. So you can choose either, you can study either. Very, very simple problem. I've actually put the codes on GitHub, so anyone can download these and run them straight off if you use Fortran, and you can get these kind of results straight out. So why is this interesting? Well, because depending on the binning resolution, you get different fractal phase space distributions. Now, that's not surprising. It's kind of like box counting. The more we zoom in, the more fractal our distribution gets. And you can see here, different bin sizes. The thing that's more interesting is depending on whether you do bins that are powers of 2 or powers of 3, you actually get completely different shapes. So this is, despite having similar numbers of bins, you're actually getting a very different distribution from using bins that are, basically dividing the domain into factors of powers of 3 or powers of 2. And this must be something to do with the underlying dynamics, but it's not clear why that is. And using a 2 or 3 give different results. And it's really this that is the kind of essence of the problem. So essentially, if you bin in powers of 2 or powers of 3, and you extrapolate to the limiting case where your bin size essentially becomes 0, that is, you use an infinite number of bins, you actually end up with a different fractal dimension prediction. Now, we're using what's called the information dimension, which is essentially like Shannon entropy, P log P of each of those bars, and dividing that by the log of the bin size. So what you see for powers of 2 is it agrees with the Kaplan-York and tends to a kind of predictable value. But for powers of 3, you get something different. And so this difference between the two is really the thing that the Snook Prize aims to understand. So that's it really. So understanding phase space is essential to understanding NEMD. The Baker map and also the continuous walk, which is even simpler, is probably the simplest way to understand this kind of multifractal nature of phase space that is underlying, all of these kind of concepts of entropy and the interesting phenomenon. These codes are essentially, the actual core of the code is 2 lines to actually do these phase maps. Everything else just loops through it and then bins the space. So it's a simple transform and then a binning. So if you want to try this out, we've got until the end of the year to solve this problem. And the idea is you take the fractal dimension and use different binning, whether it's 2 or 3, you get different results. And just here at the bottom, unfortunately, it's cut it off, is the archive link to the paper that Bill has written up. So if you search for non-equilibrium time reversible maps and walks, you'll get more information on this. Yeah, so just to summarize, basically powers of 3 or powers of 2, depending on how you divide the domain up, you get a different, basically, limiting case for the fractal dimension. And the question is, some explanation of this situation. If you can do that, you get £1,000 and the prestige. So yeah, that's it from me. Just to say, we'll aim to host another meeting next year. As I say, please, anyone who wants to help host, or has funding for kind of meetings, please let me know. And feedback suggestions, I think one definite suggestion is it was too packed today. We should have had more breaks, but anything else, any other feedbacks on how we develop as a community, please send them through. Yeah. And thank you very much for staying to the end, anyone who has.
Yeah, thank you, Ed, for organising it with James and Matthew. Very interesting.
Oh, thank you. Thank you for attending.
Cheers, everyone.
Bye.
Have a good evening.
See ya.
Bye.
Cheers. Bye.
Bye.